Reliability. Introduction to system reliability. What is reliability? The probability that a system will perform its intended function without failure over a specified period. Crucial for industries where failures can result in financial loss, safety hazard, or regulatory issues. Why is it important? In aerospace, aircraft reliability ensures passenger safety. Healthcare, medical devices like pacemakers must function flawlessly. Automotive, braking and airbag systems need high reliability. Next is the analytical system. Reliability. What statistical methods are commonly used for reliability analysis? First is the mean time between failures. It predicts the average time before failure in a system. Next is the failure mode and effects analysis, which identifies potential failures and their effects. Next is the Weibull analysis, determines failure probability over time. The last one is reliability block diagram. Model systems reliability based on component interdependencies. MTBF is a key reliability metric used to estimate the expected time between failures for a repairable system or component. It is calculated as MTBF equals total operational time over number of failures. Higher MTBF indicates a more reliable system. Next is the failure mode and effect analysis. The steps of failure mode and effects analysis is identify failure modes, analyze the effects, determine the cause, assign risk priority number or RPN, and last is develop mitigation strategies. Weibull analysis. Weibull analysis is the statistical mode used to model failure data, assess reliability, and predict the lifetime of components or systems. It provides insight into failure patterns, helping engineers improve design and maintenance strategies. This method is widely used in aerospace, automotive, and industrial application. The Weibull distribution is defined by the probability density function, where T represents time to failure, and the shape B is the shape parameter determines failure rate behavior, and the N scale which is the scale parameter is the characteristics life fail by this time, and the Y is the location parameter optional. Represents the minimum time before failures occur. The interpretation of the shape parameter helps classify failure modes, which B is less than 1. Less than 1 indicates early failures, infant mortality, where the failure rate decreases over time. B is equals to 1 corresponds to random failures with a constant failure rate, which is the exponential distribution. The B is greater than 1 signifies wear out failures where the failure rate increases over time. The reliability function describes the probability of survival beyond time. And Weibull analysis has various applications including predicting component lifetimes, optimizing maintenance schedules, investigating failures, and assessing quality control. By applying this method, engineers can make data-driven decisions to enhance system performance, extend equipment life, and minimize failures. This makes Weibull analysis a powerful tool in reliability engineering, enabling proactive management of system reliability and failure prevention. Next is the component configuration. What is the impact of component interdependence on overall system reliability? Component interdependence significantly impacts systems reliability by increasing failure propagation risk. Cascading failures occurs when one failure triggers others, reducing over reliability. Load sharing effects cause remaining components to bear extra stress, accelerating wear. Common cause failures can simultaneously affect redundant systems, negating reliability benefits. Dependent failure modes alter operating condition, making failures more likely. Software and control systems can introduce vulnerabilities, where a single sensor or algorithm error disrupts the entire system. To mitigate this risk, engineers use isolation mechanisms and, reliability analysis methods like failure and a fault tree analysis to identify address weak points. Reliability programs and implementation. How can organizations integrate reliability programs into the product development of life cycle? Organization can integrate reliability programs into the product development life cycle by embedding the reliability engineering principles at each stage. First is the concept and feasibility stage. Define reliability goals, conduct failure mode and effects analysis, and assess risk using historical failure data. Next is the design and development. Use RBD and FTI to evaluate system reliability. Incorporate redundancy and apply design for reliability principles. Next is the prototype testing. Performly high accelerated life testing and visual analysis to predict failure rates and optimize component selection. 4. Manufacturing production. Implement statistical process control to monitor quality, ensure consistency, and prevent defects that impact reliability. 5. Deployment and operation. Use PDM and CBM to detect potential failures and extend product life. 6 is the sustainment and continuous improvement. Collect the field failure data, conduct reliability growth analysis, and refine future designs based on real-world performance. What are the common challenges in implementing reliability program? First is the lack of organizational buy-in. Management may prioritize cost and time over reliability, leading to inadequate investment in reliability initiatives. Next is the limited reliability expertise, which engineers and teams may lack specialized knowledge in reliability engineering. Tools like FMEA and RBD, Visual Analysis, and HALT. Next is the insufficient data availability, which the reliability analysis requires historical failure data, which may be incomplete or unavailable. Next is the integration with product development. Reliability activities may not be seamlessly integrated into the product development, leading to late-stage reliability issues. Next is the cost and time constraints. Implementing a comprehensive reliability program requires resources which can be challenging in cost-sensitive industries. Next is the resistance to change. Teams may be resisting adopting new reliability practices due to the unfamiliarity. Next is the challenges in predictive maintenance and supply chain reliability issues and lack of continuous improvement. Need for the reliability program. Why is the reliability important in critical industries like aerospace, healthcare, and automotive? First is the aerospace. Aircraft systems must be highly reliable to ensure passenger safety and mission success. Failures in avionics, propulsions, or flight controls can lead to accidents. Reliability practices like redundant systems, failure mode and effects analysis, and predict maintenance help prevent in-flight failures. Next is the healthcare. Medical devices such as MRI machines, ventilators, and pacemakers must function flawlessly to protect patient lives. A failure in critical equipment can result in misdiagnosis and treatment delays or fatalities. Reliability testing, regulatory compliance, and preventive maintenance ensure consistent performance. Next is the automotive. Modern vehicles rely on electronic control units, which is the ECUs, braking systems, and autonomous driving features, where failures can cause accidents. Reliability ensures safety, minimize the recalls, and enhance customer trust. Next is the regulatory authority. What are the major regulatory bodies overseeing reliability standards? First is the aerospace, which is the FAA, which is the Federal Aviation Administration. Regulates aircraft reliability and maintenance through 14 CFR Part 25 or airworthiness standards. Next is the EASA, oversees the reliability and certification for European aircraft. Next is the AMIL, STD, which is a military standards for reliability prediction in defense system. Next, the healthcare and medical devices, which is the FDA, ensures medical devices reliability under 21 CFR Part 820 Quality System Regulation. Reliability Control System. How do regulations ensure product safety and reliability? Regulations ensure product safety and reliability by enforcing strict design, testing, manufacturing, and maintenance standards. They mandate risk assessment, stress testing, and quality control to minimize failures. Compliance with the industry-specific standards like ISO 26262 Automotive. FAA Part 25 Aerospace ensures durability and safety. Post-market surveillance, including failure reportings, recalls, and predictive maintenance, further enhances long-term reliability. This regulation protects consumers, prevent failures, and ensure consistent performance throughout the product's life cycle. Next is the how can reliability control systems prevent catastrophic failures. First is the reliability control system use proactive monitoring, fault detection, redundancy, and predictive maintenance to prevent catastrophic failures. Real-time monitoring system detect anomalies in critical components, allowing for early intervention. Redundancy and fail-safe mechanism ensure continued operation even a primary system fails. Predictive maintenance and condition-based monitoring use sensors and data analytics to anticipate failures before they occur. Failure mode and effect analysis and fault tree analysis help engineers identify weak points and mitigate risks during design. By integrating these strategies, reliability control systems enhance safety, minimize downtime, and prevent life-threatening failures in industries like aerospace, healthcare, and automotive. Of reliability alerts. How should an organization respond to a reliability alert? Immediate assessment and risk evaluation. Identify the affected system, component, or process. Evaluate the severity, potential failure, consequence, and safety risk. Next is the containment and temporary measures. Implement immediate safeguards. Notify relevant stakeholders, including engineers, maintenance systems, and regularity bodies. Next is the root cause analysis. Conduct failure mode and effects analysis or fault tree analysis to determine the underlying cause. Use data logs, sensors readings, and historical trends to pinpoint failure triggers. Next is the corrective and preventive actions. Develop long-term fixes such as design modification, software updates, or material changes. Implement predictive maintenance or condition-based monitoring to prevent recurrence. Next is the validation and testing. Verify the effectiveness of corrective actions through stress testing, reliability trials, and system simulation. Ensure compliance with industry standards. Next is the documentation and continuous improvement. Record findings, action, and lesson learned to refine future reliability strategies. Update training programs and operational procedures to enhance reliability awareness. Reliability is not just about preventing failures, it's about building trust in system and product.